Oh,
Oh,
never
mind.
Okay, good morning. Can you all hear me?
Yeah,
Yeah,
true.
yeah.
Okay.
Morning.
Good morning. Sorry, there was an issue just now. CK, you have you logged in into using two devices. Am I right?
Morning, Chair.
Morning. CK, did you log in with two devices? Because I see you in twice.
No, Chair.
No?
No, Chair.
Did you share a link?
Sorry?
So I think he shared a link, maybe.
No, I didn't.
Huh?
So sometimes it like becomes like that.
Oh,
Right.
okay. Oh, now it's gone. Okay, now CK's second one is gone. Okay. Okay, how was your holiday, your long weekend? Good?
Good, Chair.
Yeah,
Yep.
sure.
That's good. Okay, so last week's work was paper 6 for March 2017 and March 2018, and I also posted the answers. Do any of y'all have any questions or any questions you want to discuss on? If not, there are some questions that were asked so I wanted to go through, but it's a different paper lah. It's variant 1 of paper 2 2017. So you all have no issues with paper 6 of the ones that I gave you all last week, then we will go through that. Anyone has any questions?
No, Chair. No, Chair.
Okay, I will wait for a couple more minutes and then we will start. So the questions that were asked are from paper 2, June 2017, variant 1, so 2-1. So if you all have no issues with paper 6, then can you all also just open this paper then we will go through this together. Okay, so open, go to June 2017, variant 1. And then, we'll discuss some questions from here. Okay, does everyone have access to May-June 2017 variant 1 paper 2?
Yeah, Chair.
Those who don't have, let me know, then I will post it on the WhatsApp group. If not, I won't post.
I don't, Chair.
Okay. I will send it on the WhatsApp. Is that okay?
That works. That works.
Yeah? Okay, just give me a moment. The rest of you just look through the questions. If you have anything that you want to raise on the questions, or you think you might not know how to do, then you let me know, okay? We will start discussing soon. Okay, for those of y'all who can't have access to the paper,
I got it, Chair.
Okay. Okay, so let's start. Okay, before that, let me just quickly do attendance. Okay. CK here.
Yeah, Chair.
Okay, Daman.
Yep.
Okay. Edmund. Edmund not here. Diksha. Diksha no. Kezia.
Yeah, Chair.
Justin. Justin not here. James,
Here, Chair.
Nikita. Nikita, no. Moshuka will be late. Cedric,
I mean, here, Chair.
Desiree,
Here, Chair.
Yong Hom, not here. Zinnia. Zinnia here? Okay. Okay, so let's start. Okay, so the first question that was asked was on number 2. Okay, so everyone can see my screen, the paper.
Yeah, sure.
Okay, so on Earth, a ball is dropped and falls 2 meters in a vacuum. Okay, the acceleration of the ball at 1 meter is 10 meters per second per second. So at 1 meter, the acceleration is 10. Now the question is, what is the acceleration of the ball at 0.5 meter? Anyone wants to try? What would the acceleration be when it's at 0.5? Okay, I'll give you a couple minutes to think about it and then we will discuss. Okay, come, let's see. There is a keyword in this question. What is the keyword?
Chair, in the vacuum,
Yes. So what would that mean?
no air resistance.
Correct. No air resistance, no air particles colliding with one another. Which means, what will the acceleration be at any given point?
Chair, the same.
Yes, so it will be the same. Because number 1, it is in vacuum. So air particles not heating, no air resistance. So
So is B.
is B, yes. So you'll have the same acceleration. Okay.
So you just time it by 10.
Times what by 10? No, it's given here what? At 1 meter is 10 meters per second per second. So which means at 0.5 is also 10 lah.
Oh,
It's in
okay, sure.
vacuum. Yeah. And when we have a free falling object, what affects a free falling object? Besides air resistance, in this case, no air resistance because vacuum. But what affects a free falling object?
Gravity.
Yes, gravity. So gravitational acceleration is the same throughout, 9.8 or 10. Okay, which is why the acceleration will be 10 meters per second per second. And in this case, also because it's in a vacuum. Okay, anyone has any questions on that?
Water.
Okay. Okay. Then the next question was on question 6. Okay, so let's look at question 6. A boat is traveling at a steady speed, straight line across the surface of a lake. Okay, which statement about the boat is correct? So they're talking about resultant force. So which statement about the resultant force is correct about the boat that is traveling at steady speed?
Teacher.
Sorry?
D.
Yes, so D is when it's steady speed, so steady speed basically means that the speed is steady, there's no fluctuation or anything. So which means the resultant force on the boat is 0. Okay?
Okay, sure.
Okay, and then the next one is on question 8. Okay, so diagram shows a uniform bridge 4-meter long weighing 10,000 Newton. The bridge is pivoted at one end, a force at the other end gradually increases until the bridge begins to lift. So the lifting force here. So at a certain force, it will start to lift the bridge. So the question is, what is the lifting force as the bridge starts to move upwards? Okay, I'll give you a couple minutes to think about it. Okay, anyone has any idea on how to work this out?
Sure, is it A?
Okay, I'm gonna switch to my whiteboard. I'm gonna switch to the whiteboard, and then we can see how to
Is
work
it
it
A,
out.
sure? For number 8.
B.
Okay, can everyone see my whiteboard?
Yes,
Yeah.
sure.
Yes.
Ken,
Yes, sure.
Yeah, sure.
Yep.
can see or not?
Yes. Sure, you can't hear us, I
Can you hear
think.
me?
Yeah, sure, we can.
We can hear you, Chair.
Okay, can you all see my whiteboard? You all need to respond. You know, I wouldn't know if
Yeah,
you all can see
Yeah,
me or not.
Chair.
We can.
Can you all see the whiteboard?
Yes, sure.
Yes.
Oh, but I can't hear any of y'all, lah. Wait, let me try again. Okay, can you hear me now?
Yeah, sure. Yes,
Teacher,
sure.
we can hear.
I'm gonna try taking out the. Okay, can you hear me now?
Yes,
Yes.
sure.
Yeah, sure.
Can you hear us?
I can hear you. Okay, now. Okay, so I have a bridge and I have a lifting force. Okay, and the pivot is on the left hand side, and then I have the distance from the pivot is 4 meter. The different distance from the force to the pivot. Okay, and we know that the weight of the bridge is 10,000 Newton. Weight is acting downwards, and it's always at the center. Okay, because the center of mass is the one that pulls the weight down. So in the middle. So in the middle, if the whole bridge is 4 meter, the center of mass, which is 10,000 Newton, will be 2 meters from the pivot. Okay, so it says, what is the lifting force when we will start to see the bridge being lifted? Okay, which means at the moment the bridge is at equilibrium now. So, how do we calculate moment? So we want to look at anti-clockwise and clockwise moment. What is the formula for moment?
Force times perpendicular distance to the pivot.
Yeah, force times perpendicular distance of the force from the pivot. Okay, so that is moment. Now, this 10,000 Newton is at 2 meters from the pivot. Okay, so this gives me 20,000 Newton meter. This is the moment downwards, as in pulling it downwards. But at the same time, to lift it up, okay, to lift it up, I also have force times distance. My force, I'm not sure because that's what I want to find out to lift it up. But I know that my distance is 4. Okay, so anti-clockwise moment equals to clockwise moment. So 4x is equals to 20,000. X will equal to 5,000 Newton. So it will start being lifted up when the lifting force is 5,000 Newton. Okay, can understand?
Yeah, sure.
Yeah, sure.
Let me switch back.
Yes.
To the... Okay. Next question. Number 9. A bullet of mass 0.10 kg travels horizontally at a speed of 600. Strikes a stationary wooden block of mass 1.9 resting on a frictionless horizontal surface. The bullet stays in the block. What is the speed of the bullet and the block immediately after the impact? Okay, again, I'll give you a couple of minutes and then we will look at it.
Teacher, can you hear us?
Yes, I can hear you now.
Oh, yeah.
Y'all can hear me, right?
Yep,
Yeah,
yep.
sure.
Okay, try question 9. Okay, anyone wants to try and explain question 9?
Sure, I can.
Okay.
So um final momentum equals to initial momentum. So you can take 0.1. 0.1 times 600, you get 60.
Okay.
Then you take the 60, you divide it by 1.9 kg.
It's 60 and I divide by
1.9.
okay.
Then you get 31.58, which equals to 32, which is B, approximately 32.
That is my speed. Okay, anyone else got any other answers?
So I got A.
You got A. Wait, let me just see what A is.
30, sure.
Okay, can you explain how you got 30?
I took like the same method that CK did, like final momentum equals to like initial momentum. So for like initial, I took 600 times 0.1,
Okay.
then plus 1.9 times 0, which is 0. So like the initial momentum is 60. And the final momentum, I took, because it's joined together, so the weight will be like together. So it's 0.1 plus 1.9.
Okay.
And then that times the speed, which is like the unknown. So I used like X.
Okay.
So, and then you take 60 divided by 2, and you get 30.
Yeah. Okay. So that's how we do it number the second one, the one that Kezia mentioned. So I will explain. Okay. So according to the principle of conservation of momentum, the momentum before collision equals the momentum after collision. That is what the principle of conservation of momentum says. Okay. So momentum after collision. Let me just switch back to the whiteboard. Okay, so momentum after collision is equal to momentum before. Okay, this is according to the principle of conservation of momentum. So momentum is mass times velocity. Okay, so in this case, the bullet is mass 0.1 kg with the velocity of 600. And then I have the wooden block. Wooden block is 1.9 kg. It says that the wooden block is stationary. Okay, if you look at the question, let me just switch back. Okay, the question says that the wooden block is stationary. So stationary means that it's not moving, basically. So not moving means the velocity will be 0 for the wooden block. Okay, then it says, okay, going back to the question, it says that it travels horizontally, it strikes the wooden block, and the bullet stays in the block, which means it got stuck. Okay, it got stuck to the wooden block, essentially. Okay, so they get stuck together here after impact. So they're asking what is the speed of the wooden block and the bullet right after the impact. So we have momentum is mass times velocity. So mass times velocity. So momentum before and momentum after. So if we look at momentum before, momentum is mass times velocity. The mass of the bullet is 0.1 times with the velocity of the bullet, which is 600, plus with the momentum of the wooden block. The mass is 1.9, but the velocity is 0 because it's not moving. And that is equals to the momentum after. If you look at the momentum after, this is collision. Okay, collision because they collide and they get stuck to each other. When they get stuck to each other, again, it's mass times velocity. But now the mass is, they add up together. Why did you add up together? Because the question says that they get stuck to each other. So now the mass will be 0.1 plus with the wooden block. because they are together now. And then the velocity is what we want to find. So if I calculate this, this is 0. 0.1 times 600 is 60. Okay, 60, 0.1 and 1.9 is 2. So velocity is 60 divided 2, and it is 30 meters per second. So that will be the velocity of the wooden block and bullet together. Okay, so you must remember the principle of conservation of momentum. Anyone has any questions? Can understand? Okay, that is for question 8. Okay. Does anyone have any question on question 9? Sorry, question 9. All okay?
Yes, sure.
Okay.
Yes, sure.
Okay. Then let's look at the next one, which is, okay, y'all can scroll down, just go through. If you all have any question, ask me. If not, I'll just go to the question that had been asked, okay? Okay, if you all have no questions, let's look at question 25. Okay, 25. Just give me a moment. Okay, question 25. So they're asking the most effective method of demagnetizing a bar magnet. Okay, demagnetize a bar magnet. A bar magnet is like the simple magnet lah. Okay. So let's look at it. Okay, anyone has any idea? Anyone wants to try? What would your answer be for 25? So first one says, placing the magnet in a solenoid carrying a large alternating current, gradually decreasing the current. Placing the magnet in a solenoid carrying a large direct current, gradually decreasing the current. Number 3, placing the magnet in a solenoid that produces a magnetic field in the opposite direction to the magnet. And number 4, placing the magnet next to an identical bar magnet with its pole in the opposite direction. So what do you all think?
Sure, A.
Nature.
A will like change its domains. This is alternating current.
Please? Can you repeat that, please?
Sure, I said A because it's alternating current and it will change the domains in the magnet.
Okay, correct. Yeah, so the answer is A. So when you put it in an alternating, put the magnet in a solenoid carrying the alternating current. Now how magnets work is they have little domains in them that, that when they are magnetized, they are lined up. Okay, they are lined up in a certain direction and then they are magnetized. They are made up of little domains like that. So how to demagnetize the bar magnet is you want to, instead of lining it up, you want it to go haywire basically. So when you put it in a large alternating current, the domains will move about. Okay, they will go in different directions and that will demagnetize the bar magnet. So 25 is A. Okay. Okay. Let's look at 29. Okay. A cylinder of conducting putty has length L, diameter D, and resistance R. It is now molded into a cylinder of diameter 2D that has the same volume. By which factor does the resistance decrease? So length is L, diameter D is becoming 2D. So it's becoming bigger lah, basically. Okay, resistance R. Okay, bigger diameter that has the same volume. So by which factor does the resistance of the cylinder decrease? By how much does the resistance decrease?
Is it 2?
2. Anyone else has any other answers?
Say 8.
8. Okay, how do you get 8?
So because it increases by 2 on every side, so I just times it by 4. I actually have
Why
no
do you
clue.
by 4?
So because left, right, up, down.
Oh, okay. Okay. So 8. Anyone else? Okay, now, what is the formula for cylinder, volume of cylinder? Anyone can remember? What is the volume for cylinder?
Sure. Is it pi r square h?
Yeah, pi r square h. Okay, so now think along those lines. Pi r square h, r being the radius, and given the diameter here. So think about that formula for a while and try to see how will that change the resistance as well. So the length is going to be the same because it doesn't say anything happened to the length. So I'm going to assume that the length has no changes, which means my h, pi r square h, my h will not change. But my diameter changes. My diameter becomes double, which means my resistance, my radius of the cylinder is changing, right? Okay, and then,
So,
yes,
so doesn't the length decrease?
this the length decreases, is it?
No, sure, but it says the volume stays the same. So if the diameter decreases, doesn't the volume increase?
Is now molded into a cylinder of diameter 2d that has the same volume. Oh yeah, that's right. So the length would have to change for it to have the same volume. That's correct. Okay, so the length is going to decrease then. So what would the resistance, how would the resistance be affected? Yeah, I'm going to draw it on the board and then we can all look at it together. Just give me a second, I just want to draw it. Okay, so I have the cylinder, I have length L, I have diameter D. So what is happening now is the resistance is increasing. I mean the diameter is increasing by 2. And the length will have to decrease if the volume is the same. And we know that volume of cylinder is pi r square h. Okay. And we know that when it comes to current, R equals to V over I. When current increases, resistance decreases. For current to increase in a wire, the wire will have to have a large space to pass through, like the pipe analogy. The bigger the diameter of the pipe, the more the water can pass through. So same thing here. If let's say which means if more water can pass through, that means resistance is less. So which means if I have a cylinder like this as well, for the diameter, for the resistance to decrease, this has to be large for whatever that needs to pass through. So now the diameter is definitely increasing, which means more can pass through, which means the resistance will decrease. But we want to see how much will it decrease by. How do we do it? Anyone has any idea? I'm also not sure. So the diameter becomes 2d. Okay. If it's just d, then the volume would be pi d over 2 square h. Because radius is diameter divided 2. Okay, if it's 2d, then the volume would be pi 2d over 2 square h. This case is L. Now my length will have to change as well. So pi d square L. Anyone has any idea?
Um, sure. I tried to putting like theoretical distance and length, but I still only got a factor of 4.
Got a factor of 4.
Yeah.
Well, what do you mean by you put
So I took like diameter as 2 and then I increased it by 2. And then the length I put as 4, then I kept it 4. Oh, but it has to decrease, right?
Yeah.
So I'm not sure.
The question again. Let's just look at the question again. I have a cylinder conducting purity has length L, diameter D, and resistance R. It is now molded into a cylinder of diameter 2D that has the same volume. So the cylinder has length L, D, and R, and now it is being molded into a cylinder of 2D that has the same volume. By which factor does the resistance decrease? So the diameter is going to increase by 2, the length is going to decrease. It says that the volume is the same. So okay, I'm also unsure about it. Anyone has any thoughts on it?
No, sure.
No. Okay, I will check. I will get back to y'all on this question, okay?
Okay, sure.
Okay, let's look at the next one. Question 30. Okay. The average current during a lightning strike between a cloud and the ground is 1.5 times 10 to the power of 4 amps. The lightning releases 3 times 10 to the power of 8 joule of energy and lasts for 2 times 10 to the power negative 4 seconds. What is the average EMF between the cloud and the ground? Okay, I'll give you all a couple minutes to think about it, then we'll discuss. Okay, anyone has any thoughts?
Yes, sure.
Okay.
Just step one is to find the charge. So you rearrange the formula of I equal Q over T to Q equal I times T.
Okay.
So 1.5 times 10 to the power of 4 times that with 2.0 times 10 to the power of negative 4. The answer is 3. And then you take 3.
Okay, wait,
And
sorry.
you take,
Let me just stop you there.
okay, sure.
Can you repeat that so that I can write it on the board?
Okay, sure.
Okay. Yes.
So first we need to find charge.
Okay.
So you take 1.5 times 10 to the power of 4.
1.5 times 10 to the power of 4.
Yep. And then you times that with 2.0 times 10 to the power of negative 4.
Yeah.
Then you get negative, and then you get 3.
That's time. So
So your answer is 3.
answer is what?
3.
3. Okay.
Yep.
Okay.
So after that, give me a second. Okay, so after that, you take 3.0 times 10 to the power of 8, and then you divide it by 3.
Sorry, so I did 3.
3.0
Okay.
times 10 to the power of 8 divided by 3.
3. So this times this.
So that divided by 3.
What
Yeah.
am I doing here? I'm taking.
So you'll take. So what's that? So you're taking 3 times 10 to the power of 8.
Divided by 3.
Yes.
What am I looking for here?
You're looking for the volt EMF.
Okay.
So that will give you the answer, which is 10 times 10 to the power of 8, which is C.
Let me just go back to. So I get 3 times 10 to the power 8 divide 3, and I should get 5 times 10 to the power of 8 volts. Okay?
Yes.
That's correct. I have
So I think so.
energy over my charge. Okay, so I get my EMF. So EMF is basically potential difference. And so what I'm looking for is I look for charge first. Okay, so I take current times time because that's the formula. So 3 coulomb. And then I have my, it says here, releasing energy of 3 times 10 to the power of 8. And then I divide by this and I get 1 times 10 to the power of 8. The answer is C. Okay, anyone has any questions?
No, sure.
No? Okay, so that's how you do that. Okay, that's, what time is it now? 10:05. Okay, let me see if there are any more objective questions. Okay, there's a couple more, but I'll give you a break. It is now 10:05. Come back at 10:15, then we will continue. Okay?
Okay, sure. C.
C.
Yup.
Anyone else has any other answers? Okay, so yes, the answer is C. It reverses direction of the current in the coil after every 180-degree rotation. Okay, I'm going to show you all a video. Okay, can you all see the video? Yeah?
Yeah, sure.
Okay, so let's look at this. Okay.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings.
So the one in blue here is the commutator rings.
When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation.
Okay, so that's just a little bit about how the commutator ring works in a DC motor. So basically what happens is it will reverse the direction of the current in the coil after every 180 degree of a rotation of the coil. Okay, so the answer is C. Okay, next one. What is the purpose of a relay? Number 36. What does a relay do? A relay is a switch. So what does it do?
Should be
Small voltage, large voltage? Anyone else? Okay, let's see.
Relays are one of the most simplistic components, but they are also one of the most important, because relays are the link between low-powered digital electronics and high-powered devices. Relays allow digital circuits and digital microcontrollers to switch high-powered devices on and off. In the circuit that you can see here, this main component here, this is the relay, and a relay basically consists of a coil which builds up a magnetic field when current is passed through it. So what happens is, if I run a small amount of power through this magnetic coil, which would be inside a relay, it actually generates a small magnetic field which will actually magnetically pull a switch into the closed position to allow current to flow from the other side. And I'll demonstrate this now. What we actually have here are two different circuits, and the only thing between them is this relay. They're actually both electrically isolated, meaning that this side of the circuit is not electrically connected to this side of the circuit. So I have a DC power source here, which is running at 3 volts, and on this side of the circuit, I have an AC power supply, which could be high power. It could be the full AC mains voltage. It could be 120 or 240 volts, and it's connected to this lamp. So what happens is, by switching on this circuit, which could be me switching it on, or it could even be a digital microcontroller that switches it on based on a program or instruction that I give it. But for the sake of simplicity, I'll be turning the switch on the low powered side, and just have a look what happens. So you can see what's happened here. I flip the switch on the low powered side, which is a completely separate circuit. You can see the electrons do not flow onto this side, and the switch on this side here was magnetically attracted towards the coil on the other side, because there is now a magnetic force pulling this switch towards this closed position. So it's allowed this AC circuit to run this lamp. And the lamp is flashing because it is AC and it is running in slow motion. In real life, that lamp would be flashing so fast you wouldn't be able to see it. So let's just have a closer look at that again. Focus on this portion of the screen, and on the low powered side, I'm going to flip the switch and watch what happens. The switch was magnetically attracted towards the coil, but both of these circuits maintain complete isolation. They are two separate circuits. Now, the reason why relays are so significant is because it allows digital devices, processes and computers which run at a very low power to control high-powered electronic devices such as motors, heavy industrial machinery, and many other things, basically allowing computers and microcontrollers to interface with these much larger devices. And there is an example of this, which I will show in the future, where I used an Arduino, which is a low-powered device which runs off of 5 volts. I used an Arduino to run a bit of code that interfaced with Bluetooth from my phone. And that meant that I could send a command from my phone to the Arduino, which would then activate a relay, and then the relay would turn my bedside lamp on. And that's what relays are for, from small projects like that to huge industrial, high-powered devices. You will find relays in many, many places. They are the main component, allowing low-powered digital electronic devices to control any other high-powered device or appliance.
Okay, so from that video, what did y'all get about what a relay does? What is the function of a relay?
Is to
It's like an electrical operated switch. Electrically
yeah,
operated.
you can be like it's like the bell, right?
What do you mean by
Like the electromagnetic switch, pretty much.
okay, similar. What else? What else do you all notice about the video, or about the function of the relay?
So like how there are separate circuits, low current and high current, and they don't touch.
Okay.
Yep, and the switch closes by a attractive force between the electromagnet.
Correct. Okay, so basically we have two separate circuits, electric circuits. They don't touch each other, but with a relay, using magnetic forces, switching on one circuit will help the other circuit to also get switched on, and the other circuit has a larger current. So from a small current in one circuit, using a relay switch, I can turn on, by magnetic force, turn on another current of another circuit of a larger current. Okay, so going back to the question, what is the purpose of a relay? What would it be?
Should D.
D, yes, to use a small current to switch on a large current. So remember, relay is basically when I have two separate circuits, and then what the relay does is by switching on the circuit of the smaller current, the relay using magnetic force, okay, switches on the circuit of the larger current. Okay, so what a relay does is it helps to basically, using a small current, switch on another different circuit of a larger current. Okay, anyone have any questions on that?
No, sure.
No. Okay, then let's continue. Let me see if there's any other questions of Okay, so that is all for the questions that were asked on the multiple choice questions. Okay, and then let's look at the paper 4 questions. So there were some questions on paper 4. Okay, so, okay, let's look at this. Okay, question 8. I have a bar magnet made of metal. Okay, let's look at A first. Suggest a metal from which the bar magnet is made.
Sure,
What would we
iron.
make the bar magnet out of? Sorry?
Sure, iron.
Okay, yep. Okay. Next, I have a bar magnet being inserted into a coil of wire. The north pole and the south pole of the bar magnet are marked. Oh, what's happening now? Okay. I have the north pole, south pole marked on the magnet. And the movement of the magnet is it's going into the coil of wire. Now, the coil is connected to a galvanometer. Explain why the galvanometer deflects as the bar magnet is being inserted. What causes the deflection of the galvanometer's needle? What happens when the bar magnet is going into the coil? What is being induced?
Magnetic wave.
Yes, so I have magnetic field being created. Okay. There is a magnetic flux, so that causes the galvanometer's needle to deflect. Okay. So what happens, so it says 3 marks here. So I have magnetic field or magnetic flux created. So what happens? Well, what is the process? How do you explain what's happening? When I move the bar magnet into the coil, in and out, what happens to the magnetic field?
It decrease.
No. What is happening to the magnetic field when I move it in and out, in and out? So what is happening is the magnetic field lines, actually what happens is being cut by the coil, going in and out, forward, backwards. So the magnetic field is being cut. Okay, so what's happening is the magnetic flux is changing constantly. And because there is a change in the magnetic flux, especially when it goes really quickly, EMF is induced. So that's how that, and then that is picked up by the galvanometer. So what is happening is when we move the magnet in and out, the magnetic
Sure,
field,
you're lagging.
No, it's only you do it, not us.
Oh.
Okay. So what happens is I have a coil, I have a magnet, I move it in and out, magnetic field is produced. And then if I keep moving it in and out, the magnetic field is cut. Okay, going back and forth. And then so it changes, it keeps changing. So because of the magnetic field is changing constantly, so EMF is induced, EMF is produced, like electromotive force, voltage, in other words. So that causes the galvanometer's needle to deflect. Okay, everyone got that?
Yeah, sure. Yes, sure.
Okay, so what determines the direction of the reading on the galvanometer? So whether it goes left or right, what determines that?
So like which pole goes in first?
Yes.
Like north, south.
Correct. So which pole of the magnet enters the coil, that will determine the direction of the reading of the galvanometer. Okay. Next, describe a method for demagnetizing a bar magnet. How do we demagnetize a bar magnet? There are a few ways. You can heat the magnet with high temperature. You can hammer the magnet repeatedly.
Stroking.
Yeah. Or just now, if we looked at one of the multiple choice questions, you place the magnet in a AC current, AC coil, and then that will disrupt the domains. And then you slowly decrease the current until it becomes zero, and then all the domains is disrupted, then you also demagnetize it. Okay. So that is how we demagnetize a bar magnet. Okay. Then we have question 11. Okay. I'll let you all read this question for a while. I'll give you all a couple of minutes, then we will discuss. Okay. Okay, let's look at this question. So I have a radioactive source tested over a number of hours with a radiation detector. The readings are shown. So I have time and then the counts. Use the readings to suggest a value for background count rate during the test. So background radiation. And to determine the half-life of the sample. Okay, so just look at the readings. Try to analyze it. From 324, I'm going to 96 after an hour. And then 39 is decreasing, 21, 17, and then 21, then it's increasing to 21, and then going back to 2019, and then 2018 again. So using the readings that you see, suggest a value for background count rate. So background radiation. What do you think it is?
Should 19 counts?
Sorry?
Should 19?
19? Why 19?
Sure, because like, so like there's 21, then there's like, no, sure, there's like 20, then there's 18. So I just took the half, which is 19.
Okay, but before that, you see, it's decreasing 324 to 96, 39, 23, 21, 17, and then it goes back to 21.
Oh.
So that will be your background count rate, because from 17 suddenly it's going to 21. So that's where the count is on background radiation. So it will be during the 17 to 21 count rate. Okay, because it's increasing. Okay, can understand? Can understand why is it such?
Yeah, sure.
So we're looking at decay, it's supposed to decrease. But then suddenly there's an increase in count. So there's a high, it's usually the why there's a decrease in count rate, it would be because of the background radiation. Okay, so what will the half,
Sure.
what is the half-life? I'll just quickly switch to the whiteboard because I've written it down. Okay, what would the half-life be? Look at the numbers, I have time and I have count. Half-life is the time taken for the count to decrease by half. So what is the half-life? What is the original, what is the starting count of the particle?
Sure. 3, 2, 4.
Okay. What is half of 324?
So
162.
Okay. So from 324 to go to 162, that is half-life because the time taken for it to become half. But 162 is not in the table. Okay, let's have 162 again. What is half of 162?
81.
1.
Okay, so which means this is one half-life, this is another half-life. After 2 half-lives, then it is 81, which is somewhere here lah. Because after 1 hour is 90. So for it to be 81 means slightly after 1 hour. So for it to become 162, what would the hour be? Where would it be? Roughly estimate.
Sure, 40 minutes.
Okay, so it will be around here basically. Okay, so when it is half an hour, or no, when it is 162, sorry, half 162, because to become 81 is about slightly more than 1 hour, so we will also take 162 to be slightly more than half an hour. Okay, so your half-life will be approximately half an hour, 40 minutes, so it's an approximate lah. Okay, can you understand?
Yeah, sure.
Yeah? Okay, if you have questions, please ask. If not, I will keep going. Okay, let's look at the next question. So, hydrogen 3 has 1 proton and 2 neutrons. The nucleon number is 3. It decays by emitting beta particle. Complete the nuclide equation to show this decay. The symbol X represents the nuclide produced after the decay lah. So after the decay, it produces another nuclide, another type of particle. So how would the equation look like? Starting with hydrogen 3. Anyone have any idea? If hydrogen 3 has 1 proton and 2 neutrons, what is the number below? What would the number be down here for hydrogen?
Sure, 3.
No, below is proton number. So
Oh, yeah. Then 1.
1, okay. At the top,
3.
3.
plus 2 protons and 1 proton. So nuclear number is okay. Now, the beta particle, what is the charge? What will be the at the bottom? What will be the, not the charge? The proton number here. Top is 0. How about the bottom?
-1.
This one. So what would this be then for X, for bottom or top? What would the numbers be? Because remember, it has to be balanced. It's like a balancing a chemical reaction. The left side is the right side.
To the top is 3.
Sorry?
To the top is 3.
Top is 3, correct? Because 3 and 0 is 3. Bottom?
And the bottom will be 0.
No. No.
To 2.
2.
Wait, 2?
1.
Oh.
Okay.
Yeah, okay, now I get it.
Everyone okay so far?
Yes.
Okay. Let me switch back. Okay, let's look at the next one. The arrows in figure 11.1 shows the path of 3 alpha particles. The arrows are 3 alpha particles moving towards gold nuclei in a tin foil. Complete the path of the 3 alpha particles. So basically, what happens to the arrows lah? So you want to complete the arrow when it hits the gold nucleus. Okay, I'll give you all a couple of minutes to think about it. It wants you to complete the path of the alpha particles.
So done. So you just have to draw them, right?
Yes, we have to draw them. Okay, you want to show on my screen? Try drawing on my screen.
Okay, sure. Um, sure, is it like this? Backscatter.
Put the arrow also.
Okay, sure. Yeah, so that's it.
Okay, yeah, so that's correct. So the first one is reflected, the left, okay, back. The second one, it deflects down. Okay, and the third one is, it just goes right across. It deflects very little. Okay. Let me just give you a couple of minutes if you want to take that down. Okay, yeah, so before we go to the next one, so if you all have, so I will give you all past year papers to do every week. If you all have questions, bring it up during class, and if you all happen to do other past year papers also, we can discuss it in class. Okay, just make sure you let me know earlier so that I can prepare the paper and everything, so that the other friends can also look at it as well. Okay. Again, feel free to ask questions on different topics. If you want to revise certain topics, if you're unsure of certain things, yeah. So you want to clear as many doubts as you can, so that you can prepare for your exams. Okay. So far, how are you all with your studies for other subjects?
Sure, okay.
Okay. Okay. Okay, that's good. Okay. And then there's another question. It is from a different paper. Okay, let me just open it up. Just give me a moment. That will be the last one for today. Just give me a moment. Okay, I can't seem to find the last question. I can't find it at the moment. Okay, I will look. I'll try to, because I can't find the question. So I will look for it, and then I will either message you all about it, or we will discuss it in our next class now. Okay. Anyone has any questions for today? If not, we will end here.
No, Chair.
No, Chair.
No?
Nope.
Then that is all for today.
All right, Chair.
Okay, Chair.
Okay,
Bye,
Chair.
Chair.
Bye, Chair. Thank you.
Bye. Thank you, Chair.
Thank you, Chair.
Thank you, Chair. Bye.